Okay, we can start. Good afternoon to everyone. We are here with Professor Mendelsohn. Now today we restart again our list of seminars. We remember our economic modeling seminars. We started with, I summarize a little bit our previous events. We started with Professor Pindijk, Hill, Professor Zwart and Toll. After we had also Bergman, Professor Gollier, Van der Plug, Professor Gerlag. We have with Professor Konduri. During our conference, we'll have also Professor Nordhaus and Professor Pindijk. We restarted with Professor Metcalf and Stevens. And now we are restarting again with this new launch that is with Professor Mendelsohn. I remember that this list of seminars series is seminars organized by Italian Association of Environmental Resource Economists, Fondazione Enrico Mattei, which I am now, this very beautiful library, and University of Brescia, with the collaboration of European University Institute, University of Siena, and the Department of Environmental Science and Policy, University of Milan, and the Department of Economics and Management of University of Padua. I give you also some news related to the new next events. The next seminar will be with Professor Linsky, and in December we'll have also Professor Michael Spence. The day is the 4th of the 2nd of December, but I will give you also the new day. Another advertisement is also about our law and economics of a circular economy transition. That is this school of Italian Association of Environmental Resource Economists will be held in University of Ferrara. And also we start to give you also the new so the advertisement related to the next conference in April. You can see we are arranging, especially Elisabetta Strazzera and Simone Borghesi. So now we start with Professor Mendelsohn. As usual, I present this professor, that is a very high professor, is Edwin Warehouser, David Professor, Yale School of Forest and Environmental Studies, is also fellows of Ezra Stiles College. About his research, there is a long list of topics. He's very famous, especially relative to the evaluation of environmental economics, so relative to resource economics. He worked on some methods to evaluate natural ecosystem pollution, also including emissions of criteria, pollutants, and hazardous waste sites. And his most recent work values the impacts of greenhouse gases, including the effects of climate change on agriculture, forests, water resources, energy, and costs. Looking at his long CV, so it's very long, so I summarize a little bit. There is also some things that I would like to stress. This is what is a founding editor of Climate Change Economics, member of the editorial board Environmental Economics and Policy Studies, Doctor honoris causa at the University of Belgium in 2009, member of Connecticut Academy of Science and Engineering in 2019, and about American Environmental Resource Economics publication, he has this publication of Enduring Quality that was published in 1994 in American Economic Review with Professor William Nordhaus and Shaw. About his research, as usual, I a little bit summarize his papers. Among them, there are long, so there are more than 100 peer-review articles. Among them, there are American Economic Review, Quarterly Journal of Economics, Journal of Economic Literature, Review of Economic Statistics, Review of Environmental Economics and Policy, Energy Economics, Ecological Economics, and so on, like we know in our typical publication list of publications. There are also some books, 10 books. Among them, I have chosen some of them that are Climate Change and Agriculture. There is the impact of climate change on a regional system, Handbook on Climate Change and Agriculture, and also the last, that is the last that was published, Using Marginal Damages Environmental Policy. We have the pleasure and the honor to have here the Professor Mendelsohn. Now I leave the floor to him. Before doing this, I remember that we collect your questions at the end of the talk, that will be more or less a 1 hour talk. And after we'll send this talk to Professor Mendelsohn in order to answer at the end of the presentation. So I leave the floor to him. Thank you very much.
I'm really honored to be here. Yeah, you have an incredible, distinguished group of people who've come and given you talks on this particular seminar series. So I'm honored to be a member of this group, and it's a great pleasure to be here. So what I would like to talk about today is climate change and the impact of climate change on per capita GDP growth. So a lot of the research I've done in climate change has examined cross-sectional research, cross-sectional evidence of the impacts of climate change. But what I want to talk about today is actually a technique that other people have promoted that is basically using panel data to look at the effects of climate change. And so what I want to talk about today is some problems I see with the way that panel data has been used in the past. And I'm trying to promote the idea that we can use panel data, but perhaps we can use it better than we have to date. So right now I'm going to be talking about how to use panel data if in fact you've got a nonlinear system. And one of the things that we know a lot about climate change is that it is in fact a nonlinear system. The impact of climate change on economic systems is definitely nonlinear. So it's very important that if we can use panel methods, that we be able to look at a nonlinear system. And what I want to talk about is how to do that in practice. So let's see if I can get this going. One of the things about climate change is it causes lots of different changes all over the world. So we're not going to be talking about everything climate change does. We're going to be talking only about the direct effects of climate on the economy. So this is only one of the things we're worried about, that climate might change, temperatures might warm, precipitation patterns might change, and that somehow or another the economy itself, GDP, will be reduced by that. So that's what we're going to focus on today. But there are other effects of climate change that we're not talking about. So I don't want you to think that whatever we're talking about with respect to the economy is the only thing we should worry about. We also ought to be worrying about these non-market effects. That is, climate change is going to be affecting things which are outside the economy, on our health, our ecosystems, especially ecosystems. And those things are not going to be part of what we're talking about. So we're not going to deal with that. The other part is we're only looking today at direct effects of temperature precipitation. But climate will also be changing sea level rise, storms, and things like that. So the sea level rise and the melting of the ice sheets, those are things that also are not being captured today. So we're not talking about everything climate change might do, but we are talking about what it might do to the economy directly. So one of the things that has been true about studies we've done all over the world is there's no question that there are market sectors that are sensitive to climate. So there are parts of the economy that we know are sensitive to climate. But one of the things that we know about those things, they're important, but they're only about 10% of GDP. So agriculture, energy, water, these are things where climate change is definitely going to affect GDP. And in places where those sectors are particularly important, they may have very large effects. But one of the things that we've found is that although climate changes could be harmful to those sectors, the amount of damage that we're expecting because of that, with the climate change that we're expecting over the next century, we're talking about at most 1 to 2% of GDP. And so the sectoral data is kind of suggesting climate change is going to be a problem for GDP, but a relatively small one. And if you include adaptation and the effect of CO2 fertilization, that effect is probably going to be much less than 1% of GDP. It's probably going to be something closer to 0.1 or 0.3% of GDP. So one of the things, one of the other things we know is that the harm associated with temperature changes is going to be concentrated in the low latitudes. It's going to be concentrated in places that are already hot. So any kind of warming in places that are already hot is going to be very harmful. But it's also going to be counterbalanced by benefits you'll see in higher latitudes. So places that are already cold or cool will probably benefit from climate change. But this is just talking about the direct effects on the economy. This is not talking about other non-market effects. So this is the kind of result you get when you look at sector estimates. But one of the things that has been going on is there's been new studies that have not looked at sectors specifically. They've tried to look at GDP at large, and they've tried to argue that actually there's much larger effects of climate change. And there's two things that are behind these studies. One thing is these are panel data studies, and one of the reasons for that is that they're suggesting that weather changes, just a 1 year's worth of warmer temperatures, will actually change permanent growth rates. And if weather changes permanent growth rates, it will have very, very large effects on GDP. So if it's true that growth rates are affected, permanent growth rates are affected by just 1 year's worth of temperature change, then there's no question about it that will lead to very large changes on GDP. But in fact, what I'm going to argue today is that those claims have no validity. There's no econometric evidence that weather is in fact causing permanent changes in growth. And one of the things I'm going to argue is that part of that is because of the fact that the growth rate changes that have been found so far are temporary, and so they're not permanent. And part of it is that I'm going to argue that the use of the data so far has actually been incorrect. That is, the panel data studies that we've seen so far have not done a very good job of capturing nonlinear effects. So one of the things that is definitely true is that these arguments about growth rate effects are inconsistent with the sectoral studies. That is, we're not seeing things in the sectoral studies that would suggest these order of magnitude damages that you see in the growth studies. So why is that? Why do we, with countless, hundreds of sectoral studies, why are we not seeing something that would support the GDP studies, the aggregate studies? And what I'm arguing is that the aggregate studies actually have not been done correctly. So what do we need to know? One of the questions we need to ask is, does weather in fact change permanent growth rates? And if they change permanent growth rates, what you'd expect to see is what you see in the lower diagram below. That is, if you're going along on a nice even path of growth, and all of a sudden you have a year of hot weather, if they affected permanent growth rates, what you'd see is that the growth rate would then be much lower from then on, versus what would have happened if that high temperature had not occurred. And so you'll see that what you're looking for, if it's permanent, is an increasing effect over time. That is, you'll see the divergence of growth after that hot temperature effect is getting worse and worse. In contrast, if what you see is a temporary effect, what you'll see is in the year that you have this hot temperature, GDP went down, but in the year following, it's recovered. And the question is, what does the actual data look like? And what I'm arguing is that when you actually look at the data that the Burke study had actually used, what you find out is that the year after, you see a temperature effect that leads to a level effect, that leads to a temporary reduction. You also see that GDP recovers. So they have claimed that the growth rate effect is permanent. In fact, what their data suggests is the growth effect is a level effect. That is, 1 year of high temperatures does reduce GDP, but only reduces it for the year in which the temperature effect actually occurred. So that's one of the major flaws in their study. But so one of the things, but what I'm going to argue about today is there's another problem that's not peculiar to the Burke study. It's actually common to all the panel level studies. And so this is a generic problem of looking at panel data when you've got a nonlinear effect. And so what I'm imagining here is that you have your dependent variable, and then you have on the right-hand side, you have independent variables such as temperature. And the temperature effects, these independent variables, are not having a linear consequence, they're having a nonlinear consequence. Because one of the things we've seen in the sectoral studies and in the science is that we're expecting temperature to have a hill-shaped effect on most economic activities. But what I mean by that is there's a optimal temperature in which most economic activities are high productivity. And if it's either very cold or it's very hot relative to that optimal temperature, production falls off. So most of the evidence, in fact, all the evidence suggests that temperature is going to have that kind of consequence. That is, there's going to be an optimal temperature zone that you'd like to keep the economy in, and you'd like to keep the planet in. And if you get outside that zone, you're going to get much lower productivity. So what that's suggesting is kind of a hill-shaped response function, which is obviously nonlinear. And the question is, how do we capture that in a nonlinear model if we're using panel data? And one of the things that's tricky about nonlinear panel data is that you have two nonlinearities that you have to worry about, or that you should worry about. One of them is weather itself, that is temporary deviations from the normal weather you normally would get in a place. We all know that if weather is abnormal, if you get unusually cold weather, unusually hot weather, you get a drought, or you get unusually high amounts of precipitation leading to flooding, that weather itself causes a damage. That's independent of climate. But it's also true that we think that long-run climate has a nonlinear effect. So that as climate warms, we're expecting that as you go from a cold temperature into a temperate climate, that in fact the economy is going to improve. But as you go from a temperate climate into a super hot climate, that the economy is going to fall apart again. So there's two nonlinearities here. There's a short-run nonlinearity associated with weather, and a long-run nonlinearity associated with climate. And in principle, we're interested in both. We want to know when the weather deviates from the normal climate, what's the consequence to our local climate? We're also interested in, as climate changes, what's going to be the long-run consequence to the economy. So what we'd like to do with panel data is be able to distinguish between that short-run effect, that weather effect, and the long-run effect, the climate effect. And one of the things we know about with economics is that short-run responses and long-run responses are different. In the short run, your capital stock is held constant, and you're just able to adjust in a very limited way to short-run consequences. So short-run price elasticities are different from long-run price elasticities. Short-run income elasticities are different from long-run income elasticities. And it's also true that short-run temperature responses to weather are going to be different from long-run climate responses, because in the short run, you can't adjust that capital stock. In the long run, you can. So you would expect very different effects in the short run and long run. So it'd be nice to be able to use a panel data and measure both things at the same time. So one of the things I'm assuming is that, well, we can also test this, that is temperature has a hill-shaped effect on income, on GDP, income per capita. So income per capita is what we're measuring as GDP per capita is what we're using as our measure of income. And what that implies is that warming is likely to be beneficial to cool countries, countries that are like in the northern latitudes, like the Scandinavian countries, but it's going to be harmful to hot countries. So as you move towards Italy and the temperatures get much hotter, warming might be immediately harmful. And as you move even further south, as you go beyond the Mediterranean climates and into equatorial climates, we're expecting the damages to be even higher. So what we're expecting is that the long-term effects are going to be hill-shaped. We're also expecting the short-term effects are going to be hill-shaped. And one of the things that we're expecting also is that the short-term effects are likely to be bigger than the long-term effects, because in the short term, you cannot adjust your capital stock, but in the long term, you can. And so you have more flexibility in the long term than you have in the short term. And one of the things I'm going to argue is that if you can measure these short-term and long-term effects separately, one of the things we'll see is that they're different. And then in particular, we're going to find out that the short-term effects are roughly twice the size of the long-term effects. That is, the harm of an immediate sudden effect of temperature is going to be much bigger than the long-term expected effect of a climate change. So that's the results we're going to see when we actually do this panel analysis correctly. So what I want to try to do is go through a complicated panel model and distinguish short-run and long-run effects. And I'm going to try to use some nomenclature throughout this that may be unfamiliar. So I'm going to try to go over this first. The VIT is the variable that you actually observe in any one time period. And it's going to be composed of two things. It's composed of the mean that you expect to see at a location I, plus the deviation that you expect to see over time at that location. So what you observe at any one moment is always the mean of that variable at that location, plus the deviations, this delta VIT, that you'll see at that location each period. So VI is the expected value of the variables. And what you expect is the expected value of deviations. By this definition, how we're defining deviations, the expected value of deviations is 0. So this is just trying to get the nomenclature I'm using in this talk a little bit clearer. So what's the theory? The theory is that we think that climate, the long-term effect of GDP on climate, if climate's an independent variable, we believe that's going to be hill-shaped. And so we want to have a quadratic function to try to capture that hill. And so one of our hypotheses is that the alpha-2, the parameter that you see on temperature squared, for example, or even on precipitation squared, we're expecting that parameter to be negative. So that's something we can test. But one of the things we're not expecting to see is that it'll be 0. That is, we're not expecting that temperature is going to have a linear effect on GDP. We're actually expecting this hill-shaped effect. And what that means is that the marginal effect of long-term temperature, so that's the expected value of temperature at every location, we're expecting that to be linear. So that the marginal value is a line that at first is positive if you're in a cold zone, goes to 0 at some optimal temperature for the economy. And then if you go above that temperature for the economy, it goes negative. So it becomes harmful once you pass the optimal temperature for the climate. So that's the underlying hypothesis, is that we're dealing with a nonlinear climate problem, and that we can approximate that at least roughly with a quadratic function. So that's the underlying theory about the climate. Now, what's going on with weather deviations? What should be true about a weather deviation is that when the weather happens to be exactly at the climate, that is, when it just happens the deviations are 0, what we expect is that the effect of weather deviations and climate deviations will be the same. So this is a theoretical proposition. And the reason we're arguing that is that at that moment when the deviations are 0, the capital stock has been optimized for that particular temperature, because that's the capital stock that the climate's adjusted to. So the weather at that moment is also got the optimal climate stock. So the weather effect, the effect of weather when the deviations are near 0, ought to be exactly the same as the climate effect. So you can measure the short-term effect at the long-term climate effect when the deviations are zero. Or to put this a little more precisely, since the intertemporal data is trying to measure the short-term effect, when the deviations are zero, it just happens at that moment, it's also measuring the long-term effect. But one of the things that's true about this theory is it's saying, actually, the long-term effect is going to vary depending on the climate. So the long-term effect should be different at different climates. So if the long-term effect is hill-shaped, different places should have different marginal effects when the deviations go to zero. So this turns out to be very useful for tying together what we're expecting in the long term and what we're expecting in the short term. Because the short term, when the deviations are zero, the short-term effect's got to be equal to this long-term effect. But this long-term effect itself is quadratic, which means that the marginal part of that long-term effect is linear. So what does this mean in terms of what does this look like? It means that if you're looking at the long-term effect, what you expect is that GDP or income should fall as temperatures climb. But what you're expecting is the marginal effect of this is actually going to be equal to that short-term effect when it happens that the short-term temperatures happens to be the same as the long-term temperature. But we also believe that short-term effects, short-term changes from temperature, when the short-term deviation is not zero, but it's non-zero, the effects will deviate away from the long-term consequence. That is, we believe weather itself has an effect. And we're expecting that the effect of weather is going to be steeper than the effect of climate. So the underlying model is that we're going to have these short-term effects that vary by location, and these long-term effects that you can describe across locations that are based on this long downward line. And then at each location, you'll see short-term effects around that long-term consequence. So this is what a visual of what we expect the short-term intertemporal effects are going to look like relative to the long-term effect. And what that means from perspective of trying to model the short-term effect is when the deviation is zero, the short-term effect, this delta y, delta x, should be equal to the long-term effect. So when deviations are zero, that's what should happen. But when deviations are non-zero, then it turns out that you ought to see an additional effect that's caused by the weather deviation itself. And so you go from the effect of just being a linear term to adding this additional weather term. And then to get back to the underlying effect, not just looking at the marginal, but the actual effect, the change in income that you should expect to see, observed change in income you expect to see, or the deviation in income you expect to see in each time period, therefore should have to be equal to this, a linear term of the deviation, plus an interaction term between the mean of the temperature and the deviation, plus the squared term of the temperature deviation. So what I'm trying to derive here is a model of how the data ought to behave, how you should expect the panel data to behave, if in fact both the short-term effect, the weather effect, and the climate effect are both nonlinear. The result you should get is a data generation process that looks like the bottom equation that I have on this chart. The deviation should be equal to a function of the linear term, this interaction term, and the square of the deviation term. So this is different from the model that's been estimated in the literature. And so what I'm arguing is this is a superior model than the one that's been used in the literature, because this particular model leads you back to both a short-term linear term and a long-term effect. You can derive a short-term effect and a long-term effect from this model. If you use an arbitrary data generating process, which the literature has done, you cannot get back to the underlying short-run and long-run response functions. They're unknown. So this is the big innovation I'm trying to make in the panel data analysis, is to use a data generation process that actually follows from known short run and long run consequent models. That is, you can link short run and long run models back to this. So what does this mean? It means the correct model that you ought to be running when you run a panel data is the model on the top. That is, you should be looking at the deviation in the dependent variable should be a linear function of the deviation in the independent variables, an interaction term between the mean and the deviation, plus the square of the deviation of the independent variables. And the first two terms, this beta 1 and beta 2, define the long run effect, the long run marginal effect. And the entire equation defines exactly what the short run effect, what you expect weather to do across the panel. So if you use this functional form, it turns out that you can estimate both short run and long run effects using panel data. So this is an innovation that I'm encouraging all panel studies, at least especially the ones that nonlinear panel studies, that they all use this as the correct functional form for their models. So you want to contrast this with what the panel literature has actually done. And so what the panel literature has actually done is, instead of using this functional form, where you're looking at deviations as a function of deviations and deviation squared and an intermediate term, instead they have looked and argued that the observations should be a function of a linear term and the square of that linear term, plus a fixed effect. And if you do this is this traditional way that panel models have been estimated. Then when you actually look at the underlying terms, if you break this down, so what does an observation mean? Well, an observation is just its mean plus the deviation. Then it turns out you get this second equation underlying this model. That's just substituting in for what these things are. But when you take the partial derivative of this model, one of the things you find out is that a standing assumption of this model is that the long run effect and the short run effect are identical. And not only that, but they're equal to beta 1 plus beta 2 times x1 plus delta x. And it turns out there's problems with that. There's two problems with it. First of all, assuming that the long run and short run effects are the same throughout all the data is a very strong assumption, because in general, we never think short run and long run effects are identical. And second, this model doesn't really make much sense, because it's arguing that the long run effect is actually a function of the deviations. But we know that long run effect is not a function of deviations. It's just a function of the expected values of parameters. So there's serious problems with the standard model that's been used in the literature. The literature has basically picked a functional form that does not make any sense when you actually look at its underlying features. So what happens when you apply the model that's in the literature? Well, it turns out when you apply that model in the literature and you apply the fixed effect, so you start with the model as it's written. When you apply the fixed effects, what you're effectively doing is subtracting the expected value of each parameter from each of those terms. It turns out what you end up with is a very odd looking equation, which is this next equation here, which says that the deviation is a linear function of the deviation, but then it's a function of this expression that has three terms in it. And it's interesting that the three terms includes the interaction term between the mean and the deviation. It includes the square of the deviation and minus the expected value of the square of the deviation. So curiously enough, this beta 2 term does not end up being anything that you would normally be able to recognize. It's actually got 3 terms in it. If the delta x squared and the minus expected value of delta x squared, if they canceled out, then this expression would just be the linear term plus the interaction term. But in fact, they don't always cancel out. So it turns out this model actually doesn't work very well for estimating the interaction term. And it doesn't work very well for trying to estimate either a short run or a long run model, because in some ways it has confused short run and long run effects together. So what I'm arguing is the nonlinear model that's been used in the panel literature has basically been biased and poorly construed, so that you actually cannot figure out what is the short run and long run effects that underlie that model. So one of the things I've done then is said, okay, this is misspecified. What happens if you specify it correctly and use some actual data? What kind of results do you actually see then with the data? So I've gone back to the data that Del Jones and Olkin first developed for country level data. And it's the same data that the Burke et al. Paper is written with. And what we're looking at as the dependent variable in this case is the change in income in any one period. So it's the income, the observed income minus last period's income. It's what's different about income this period. And you could estimate this with the Del Jones approach with a linear model, or you can use the Burke et al. Paper and use a quadratic model of that with annual weather and country and time and fixed effects in it. So that's what I've done. I've tried to say, okay, what happens if we actually use this data? And this is what the model looks like. This is what the results look like. If you use the linear model alone, actually, I don't show you the linear model alone. I've just shown you the standard model. So what this is showing you is the standard model, which is what I'm calling is the standard model in the literature. It's got a linear and a squared term, and those linear and squared terms are on the observed variables. And if you do that, what you find out with this data is that the coefficients for poor countries, for the half of the world that's less than the median per capita income, all you get from that, you get a hill-shaped response function, but all the parameters are not different from 0. If you use the rich countries, then you get a hill-shaped response function, where in fact the quadratic term is now significant. But they're both hill-shaped. On the contrast, if you use the preferred model, the one that I'm arguing is the correct model, then it turns out you get 2 response functions, not just 1. You get the squared term on the parameters, which is the weather effect, and that's showing you what consequence you get from weather. But you also get this interaction term. And what the interaction term is giving you is the response function to climate. So you're getting 2 response functions. The linear term applies to both of them, but the squared term applies to the weather consequence, and the interaction term actually gives you the shape of the climate response, the long-term climate response. And what it's showing you is that the long-term climate response is actually a flatter response function than the weather response function is. And what that means is when you look at that marginal response function, it's a flatter marginal line, whereas when you look at the weather response, you're getting very steep lines. And the other part that it's telling you is that the weather response is going to vary over locations depending on the mean temperature of those locations. So you're going to get different responses depending on what the underlying climate looks like. So that's what the preferred model is telling you. What the standard model is telling you is just that weather has a hill-shaped response function over space, over time. So one of the things that's interesting about that is if you just use fixed effects, you don't have a trend variable in there, just use fixed effects alone. When you use the standard model, you get a marginal effect that's equal to 2.35 minus 0.05 times temperature for poor countries, and then you get a smaller effect for rich countries. The preferred model actually has, for its long run effects, this is what we're expecting the long run consequences. It turns out the long run consequences actually look very similar. So one of the things that's interesting about this is that if you just use fixed effects and not country-specific trends, the standard model and what I'm calling the preferred model actually suggest similar effects, which means that the standard model, if you estimate this with just fixed effects, actually seems to be picking up not a weather effect at all, but it's actually picking up the long-term effect. It's measuring what the preferred model is saying the long-term effect looks like. So that is an interesting result in itself. The other thing you find out is that, of course, the preferred model results are saying that you're getting, on top of this long-run effect, you're getting much steeper short-run effects. So one of the things that's true about both models is they're saying that it happens, the poor countries and the rich countries appear to have hill-shaped response functions, but the peak temperature of those two hills is not the same. The peak temperature for the poor countries is around 23 degrees, whereas the peak temperature for the rich countries is around 12 degrees. So what the results are suggesting is that these two sets of countries have very different optimal temperatures. And it's interesting because most of the poor countries happen to be in hotter locations. Most of the rich countries happen to be in cooler locations. So it somehow, one of the possible things, one of the questions is why do they have different peak temperatures? This study can't tell you why, but one hypothesis is that just simply being in a long-term, being for a long time, developing in a hot temperature, you may have developed an economy that is actually ideal for a hot temperature. Whereas other countries that have developed for being in a cool temperature have actually developed their economy so that being in a cool temperature is optimal. That's a hypothesis, but one thing that is very clear is that the peaks of these two sets of countries is quite different. And so what does that mean? It means if they have peaks, one of the things it's telling you is if a country happens to be cooler than the peak and you get climate change, it's going to be rising up the hill. If the country is hotter than the peak and you get climate change, it's going to be falling off the hill. So who benefits from this, who gets harmed, all depends on where they happen to be and what their mean temperature happens to be relative to this peak. What else is the analysis saying? The analysis is also saying we're seeing short-run effects that have a steeper response than the long-run effect. So getting sudden deviations in temperature is far more harmful than getting long-term changes in temperature. And it appears to be about twice as harmful. So these are the two results that we're getting out of this result. And whether you happen to be benefiting or being hurt depends on where you are relative to this. A lot of the countries, the poor countries, and here's another interesting result, is poor countries actually benefit more from being in cool temperatures, and rich countries actually are hurt more by being in hot temperatures. So they both have different response function. If you happen to be a poor country in a cool temperature, you'll be better off for it than if you're a rich country. But if you're in a hot temperature, you're much better off being a poor country than being a rich country. So this is an interesting result that we were not that sensitive to beforehand. So what does the actual data look like when you actually take those parameters we had just estimated in the preferred model? This is what these two response functions look like. What we're looking here is the marginal temperature response relative to temperature with respect to percentage changes in GDP. So when I was arguing before that the poor countries have a peak temperature of 23, what that means is this marginal temperature response goes to 0 at 23, which means you've reached the peak of the hill. If you're on the left side, if you happen to be a cool country and you're poor, and for example, you're at 10 degrees, and you get a little warmer, it turns out you benefit. Your income is going up. It's going up at a declining rate, but it's rising if you get warmer. If you're on a weather change, if you're talking about a sudden change in weather, it turns out this is a much steeper function. So you also would benefit. If you're a poor country in a cold place, you get a warm year, you will benefit if it's a relatively small change, if it's up to 2 degrees. But if it's more than 2 degrees, if you went out to further than that, you would actually start to be hurt, because you'd actually be falling down this temporary short-run response function into a negative territory. But your short-run response functions are different depending on where your climate is. So if you're poor and your climate is 10 degrees, you're on this leftmost short-run response function. If your climate happens to be 20, you'll be on this middle short-run response function. And if your climate happened to be 30 degrees, you're on this far right climate response function. And one of the things you can see is the effect of weather depends a lot on the climate you happen to be in. So one of the things this is telling you is weather responses vary a lot across space and time, both. The climate responses don't vary across time because over time, the climate is constant. But it's quite clear with climate change, you'll be moving down this curve. Rich countries have a flatter sloped response function than poor countries. But rich countries are starting at a different spot than where poor countries are starting. So their peak is around 12 degrees. That's where the marginal effect goes to 0. If they slide to being as hot as some of the hottest countries are, it turns out they get bigger losses. You get losses of 1.2% versus 0.5% at 30 degrees. So rich countries are actually more sensitive to cold temperatures. Poor countries are more sensitive to rich countries are more sensitive to hot temperatures. Cold countries are much more sensitive to cold temperatures. But cold temperatures are beneficial, hot temperatures are harmful. So what the analysis using this different panel model approach is saying is you are starting to distinguish between short-run and long-run effects. You can also distinguish between rich country and poor country effects. And one of the things you're seeing is that all the responses to temperature are hill-shaped, but the hill-shaped response function is different for poor and rich countries. So if you're looking at marginal temperature climate effects, so this is looking at the effect of climate, and you're a poor country and you're in a cold place, you'll get benefits. You'll be benefited by that by a lot. If you're a rich country, you'll also benefit, but you'll only benefit a little bit. If you're at 20 degrees, on the other hand, a poor country will still benefit, but just a little bit. At 20 degrees, rich countries now will be taking a loss if there's a marginal temperature change. And at very hot temperatures, if you're getting up into 30 degrees, everybody takes a loss. So poor countries will take a 0.6% loss, and rich countries would be taking a 1.2% loss. So what you're seeing is temperature effects will vary a great deal depending on what your underlying climate looks like. The other thing that you're seeing is that, another thing that you're seeing is that if you did this analysis differently, if instead of doing simply panel fixed effects, you also included a trend variable and a trend variable squared by country, you actually get very different results. So I did this again with the trend and the trend squared, because if you actually look at the Burke analysis, that's what they've done. So this analysis is trying to reproduce more carefully exactly what the Burke analysis did do, which is they put trend and trend squared variables in for each country. And it turns out that does not change the results of the preferred model very much, but it does change the results of the standard model, of their model. It does change their results a lot. So one of the things that's true now is when you try to compare their model to the long-term model of the preferred model, it's no longer the same. In fact, if you look at these two things, given the way they've estimated their model, it's now true that their model is actually starting to resemble the short-term model. The coefficients of their model are looking closer to the coefficients of the short-run model rather than the long-run model. So when you include these country time trends variables, the coefficients of the Burke et al. Approach lead to coefficients that actually look like the short-run effects, but the standard model are quite different from that. So that you're getting results which now don't look at all like long-term effects. They're starting to look closer to short-run effects, and their model doesn't actually make any sense at all compared to the long-run model. But when you're looking at the preferred model results, what you're finding is the preferred model results actually are fairly stable, and they're pretty much the same as they were when you just used regular fixed effects. So what does all this mean? It means that it's an exciting thing and a positive thing. You can use panel data to estimate short-run and long-run effects if you use the right functional form. And if you use the right functional form, what you can do is capture both the nonlinear effect of the long-term part and the nonlinear effect of the short-run using the panel data. So this is kind of an exciting innovation. And what you find is what is something that's more consistent with the sectoral studies. You're finding magnitudes of effects which are quite consistent with the short-run studies. You're finding the hill-shaped response function, which is also consistent with the short-run, the sectoral studies. And you're finding that the responses in rich countries and poor countries are different. There may be lots of reasons why the response functions in rich countries and poor countries are different. So I don't know why that's true, but one of the things that this is saying is they are true. Another explanation why they might be different is that poor countries have a much larger fraction of their economy in climate sensitive sectors. So in agriculture in particular. And so it could be that because that dominates, has a bigger role in the GDP of poor countries, they have a different response function because of that. What is it also saying? It's saying that if you look at the overall global effect, if you apply this response function across every country and you look at sort of what would happen if you just get a marginal increase in temperature, what it actually suggests is that it leads to a positive, very small consequence on GDP. So if you use every country, you find a small positive effect on GDP. If you just use the data, and why are you seeing that? It turns out if you just use the data for poor countries, you're getting a much bigger positive effect for poor countries, but you're also seeing a negative effect for rich countries. So this 0.03% effect is a weighted response from poor countries and rich countries. So what this is saying is that, as far as we can tell, poor countries actually might benefit from warming, even though they're in warmer temperatures. The response function they've got is different, and so they may actually benefit. Whereas it looks like rich countries may actually lose some GDP on the margin because of warming, and the size of that loss looks like it's about 0.1% of GDP. One of the things that's true about non-marginal changes is that we expect the bigger the change in temperature, the more harmful the effect's going to be. So this response is just talking about a 1 degree increase. But if you start talking about 2, 3, 4 degrees, what we're expecting is the marginal effect will become ever more harmful, because our marginal response functions were all linear and they all go down, which means that as you move to warmer and warmer worlds, this is going to get, the effects are going to get worse and worse. So the benefits are going to get smaller and the harmful effects will get larger. So what this is implying is the kind of results we're getting from the sectoral study, that the effect of temperature on GDP, it's very likely they're going to be small. That is, small relative to the size of GDP. 0.1 per 3% change, or even a minus 0.08% chance, is not a small number when you multiply it by the GDP of all the rich countries in the world. You're talking about $40 trillion or something of rich country income and $30 trillion of poor country income. Or you're talking about a lot. These are still large numbers. There's still lots of damage, but they're small relative to the size of GDP. But these results don't count the effect of sea level rise. So this is not the entire consequence of climate change. And they're not measuring non-market effects either. So this is just measuring the effect directly on GDP. And what it's suggesting is that temperature changes are not going to change the path of GDP very much. They're just going to lower GDP a little bit. That's not where most of the damage from climate change is going to be. If there's huge damages from climate change, it's going to come from sea level rise effects, or it's going to be coming from non-market effects. Okay, so that's the presentation. Thank you. I'm looking forward to your comments.
Well, it's very interesting, your presentation, also because in my view there are some novelties, so later relatives to some our topics, especially in my mind. I'm thinking in my mind something related to the damage function in general. So if I take into account this, I should take into account that there are two different types of effects, short run and long run. If I think to integrated assessment model, I have to take into account the long run effect, and to maybe to take into account also this hill effect of the peaks in different geographical areas. Yes. So also you answer to one of my questions, because in my mind, during your presentation, I thought that one of the points is in order to do this estimation, I should take into account also where I am. So if I am in the northern of Europe, is different because the two variables are temperature and income, but I should take into account all this, but you did. two questions in my mind are, one is in adaptation. So what about adaptation in this, especially in data? So if I take into account the long run effect, there is also embedded also an adaptation effect. And the second really is also, is again this idea. This is a new manner in order to take into account, I should change also the damage function now to adapt to these new results. So the new insight that comes from your research.
Yes, so just to respond to that, so in the long run, the reason why the long run responses are different from short run is precisely because of adaptation. So this is measuring the fact that adaptation matters.
Perfect. So I'm capturing exactly this effect.
Yes,
okay.
That's exactly right. That's exactly what you're capturing. Is that's the difference between a long run response and a short run.
Okay. And so perfect. So in doing a change of the damage function, I should take into account your second the long run effect, and especially your preferred your best choice in your model.
Yes.
Okay. Perfect. So this could be useful for us for our research.
Totally. Now, yes, it's directly useful. Yes.
Thank you very much. Now I know that there is Simone Borghesi. I asked Simone if he would like to, if he's able to use his, to switch on his camera. Simone is here. Simone is here.
Okay.
Perfect.
Great. Sorry, I'm on multiple computers trying to. Can you hear me?
Yes.
Okay, great. Thank you, Professor, for your very interesting presentation. It was fascinating. And I was trying to figure out while you were speaking whether the curves might shift or change their positions over time. Let me explain this. If I got it right, there are two bell-shaped curves, one for the poor and one for the rich.
Right.
So as the poor get richer, does the curve shift to the left?
That's a great question.
And also in terms of playing with the curves, I was wondering whether the two curves have different heights. Maybe you said it, but I might have lost for technical reasons. Whether the two heights are different, and so whether as I move from poor to rich, the curve also gets flatter, or whether it shifts upwards. You know, this is something that comes to my mind because I've been working a lot on the environmental cousins curve in the past. And so when I see this kind of curves, this resemble the literature over there.
So that's an excellent question. And I guess I'd have to say, I can't answer that, but that would be an important question for future research. What you're asking is, if you have economic development, what you're expecting is poor countries are going to gradually move and become rich countries. If that was a function of absolute income, then as soon as they become just as rich as a rich country, they ought to look like this. And so I believe that that's most of the difference, is that it's economic development. And what's happening with economic development is that you're becoming less and less vulnerable to changes in agriculture, because it's a smaller and smaller fraction of your GDP. And so your economy is changing. And you may be developing a new sensitivity for other reasons. For example, rich countries who are going to have spend a lot of money on cooling. And as the country becomes richer, it's therefore going to be spending a vast more money on trying to do cooling than it was before. And so if you're in a hot place, that's going to be especially burdensome to you. And so you might become much more like the rich countries because of those changes as well. So I'm guessing that it is economic development that makes you change. Exactly what the dynamics of that look like, this study can't do that because it's just looking at two sets of countries. But it's possible if we did more studies, we could try to piece that together. For example, maybe breaking up the world not into two groups, but into 4 groups, you know, break up into very poor, medium poor, low middle income, high middle income, and rich. We might be able to start to sort that question out, because you could see it as countries move in different levels of development, are they actually starting to approach each other? I don't have an answer to that. It's a great question, but I think that's something that further studies could actually reveal. We could get at that. We could get to an answer about that question. It's definitely it's worth studying that. This analysis suggests that's an important topic, because it suggests that economic development itself might change climate sensitivity. That's a hypothesis that Professor Schelling had way back in the 90s. He actually made the argument that as countries develop, actually the argument he made is they might become more climate insensitive because of the reduction in agriculture as a fraction of the GDP. But it might be that actually they might become more climate sensitive because of other changes that he didn't take into account, but that might be more important. That this analysis suggests they actually might become more sensitive, not less, to hot temperatures. But that's a super important thing to study. Hopefully someone will pick this up and say, I'm going to do that. I want to find out the answer to that question.
Thanks a lot. Thanks a lot.
Now there is a question from Davide Vaccari. Now again with a camera, if it's possible.
Thank you very much, Professor, for your presentation. Okay, here I am.
There you are. Okay.
Hello, everyone. So I was wondering at the beginning of your presentation if you considered deep learning methods for forecasting temperatures. For example, I was thinking about recurrent neural networks for time series analysis. But then I kind of understood that maybe for the type of study you're doing, you indirectly answer to that question during your presentation, and is that you want your results to be traced back to your functions, which is something that cannot be done with machine learning right now. But maybe you could use a little bit of machine learning. So still, I was curious if you thought about that, or if you think there could be space for research to maybe get more detailed analysis using this kind of models.
Well, one of the things that machine learning is particularly good at is using vast data sets to try to discern patterns inside those data sets. And one of the things that economists are not used to taking advantage of are these gigantic data sets. So I think this is something that is going to be available to your generation. It was not available to mine. is that all of a sudden you're going to have these data sets to look at, because they're being collected by the internet companies. There's these opportunities to see a lot more detail that might be able to help you uncover things which are currently not visible to us. Now, whether you're going to uncover different aggregate things or not, I'm not sure that's where the benefits are going to be. I'm guessing the benefits are likely to be in the extra refined detail that you're going to be able to see that we cannot see now. For example, we don't have much of a clue what's going on with individual people and how they're being affected. But I think that's something that is going to be much more available to you as time goes on. And you'll be able to see within country consequences that are invisible to us at the moment, and be able to say more about, if climate changed, who's going to win from that and who's going to lose. So I think there's going to be things that will open up to you, and especially about the environment in general, that you're going to get more detail, and that's going to let you see things that we can't deal with, and it might let you control things that we can't control either. There's lots of non-point sources, pollution that we don't have a chance of controlling at the moment. because we just can't see it. I think in the future, you're going to be able to see those things. And the idea is that you'll be able to control them then. So things which we control, right now we're kind of regulating only large point sources. And one of the things that I think you'll see with this more refined data is you'll actually be able to control non-point sources as well, because everybody's behavior is going to be visible. And right now, everybody's hidden. And so they're safe from us, but in the future, they won't be. So I think that actually opens up things to do a better job with things which we can't handle right now on some dimensions of environmental protection.
Yeah, perfect. Thank you very much. That's exactly what I was thinking about, maybe expanding even on your research using machine learning models, even at a more particular level, for example, intra-country, Yes.
And looking at much more at the behavior of people at a much more refined level, and realizing you actually might be able to learn something from that behavior and regulate.
Thank you
as well.
Thank you.
Okay, thank you, David. Now we have other questions. So if you have time, so
Can you read the questions to me? Is that possible?
me?
Yeah.
Oh yes, but I don't have. Maybe Elena. I ask Elena if she.
Oh, here they are. Okay.
Yeah, okay.
Hello, can you hear me?
Yes.
Okay, perfect. I'll be the reading voice. So the question number one is, I wonder whether the assumption by BHM on the equivalence of long and short effects is specific to the choice of a quadratic model or is more general. For example, would the assumption still be there if I would estimate a logarithmic, exponential, or higher order polynomial model rather than the quadratic model?
So that's a great question. So one of the things that you should be clear is that the criticism I'm levying against BHM is not those three authors. They took a model that exists in the literature. They didn't create this model. This is a problem for all the panel literature, not just people that have studied climate problems. So it turns out, no, I originally first looked at this model thinking along the lines of a polynomial. When you have a polynomial, the whole process gets much more complicated. But it's still true that the traditional functional form that the literature has picked would make the short run and long run effects identical. So it's the function. It's the problem is not whether it's quadratic or more complicated. The problem is that it's quadratic function of the observations, rather than the more sophisticated model, which is assuming that the underlying function is a function of the marginal effect of the long-term effect, plus with an interaction term, plus whatever effect the weather's got. So there's sort of making the model more complicated by going to a polynomial rather than a quadratic is definitely something worth exploring. So that is a point that's worth talking about by itself. That's something worth doing, because there are some indications that this hill-shaped thing is may not be symmetric, and so making the model have more terms in it, a cubic term, for example, might make sense. But the problem is not the problem in the literature is the underlying functional form, that they assumed this nonlinearity was a function of the observations, the observed variables, rather than understanding that actually there's a long run effect, which is a function of the mean of the variables, and there's a short run effect, which is a function of the intertemporal variations. It's failure to understand the nonlinear effects in the short run and the nonlinear effects in the long run alter the functional form in different ways. That's where the assumption, that's where the literature has made a mistake. And it's not BHM in particular, it's the entire nonlinear panel literature. That includes studies that are about very different economic topics that had nothing to do with climate. So the problem in the panel literature is a bigger one. It's not specific to either one study or just climate studies. It's actually all the studies that have used panel literature with nonlinear functional forms have all made this mistake.
Okay, perfect. So now we have another question. Okay. Okay. I'm looking at the. Is the approach you have presented potentially be applicable to trade dynamics? For example, impacts of climate change on trade flows. This is a question.
Yes, yes. Anything that's got to do with climate is going to. This is going to be relevant too, because we're in. If as long as you're talking about a climate change or looking across space and looking at climate that's significantly different from one space to another, we're expecting it to be nonlinear. If you were looking just within Europe, within a narrower range of climates, it's possible it might be linear within that domain, in which case you can use a linear model. And the linear models, there's nothing wrong with linear models. It's only when you start to go to nonlinear functional forms that you have to start dealing with this much more complicated phenomenon I'm trying to talk about. But yes, in principle, it would apply to anything that's nonlinear, whether it's the climate variable or whether it's some other independent variable that is also nonlinear.
Okay, perfect. So there is another one, which is this one. Does the technological progress could have an effect on this model? If yes, which kind of effect? And is it worth of mention? Okay, we conclude. Thank you for your interesting presentation, but this is the question.
So the question is about technical progress?
Yes, exactly. If the technological process could have an effect on this model. Yes.
Yes, yeah, in principle, yes. And so you'd want it, there's no question you should be interested in asking the question whether climate change can affect technical progress or can affect anything that would affect long-term growth. Asking that question is an excellent thing to do. I'm not discouraging you. All I was trying to talk about in this paper was that we haven't done a good job of it, that we haven't really investigated whether climate change, or we haven't found that climate change has actually changed economic growth rates or technical progress. But those are questions that need to be asked. You want to explore that. So you need to find some way to measure technical progress. Either using traditional methods like panel or using some kind of measure of productivity growth over time. You need some kind of a measure of that. And then you need to see, well, can I see whether climate alters that technological progress or not, or whether climate change does? So that's a great question to ask. And I strongly encourage you to probe that. We want to know the answer.
We know. Okay, but last two questions if you have time. So one is this one, which is I try to summarize. I was wondering whether considering different subnational levels, such as regions, would lead to different results, given the significant climate variability that might be inside the countries covering different latitudes. For example, Italy or South America. This is more related to the
yes.
So the country level, yeah.
Well, I think the answer to that is it probably does matter. And the reason I would say that is that when we've done sectoral studies, in particular the studies of agriculture, they've been different in every continent. The way climate affects agriculture in every continent has been different. So I think it actually is important to do regional studies, especially sort of continental scale regional studies. Because there could be lots of reasons why the climate is having different consequences. One thing is that there's huge differences in how climate behaves if you're near an equatorial zone versus you're in a temperate zone. In the temperate zone, we have this very clear winter and then a single growing season in the summer, spring to fall. But in the tropics, it turns out the weather's warm all year long. And so you don't get that same seasonal variation. And so what you see in the tropics is that agriculture thrives when there's a lot of precipitation. And so it's much more precipitation driven than we see in the temperate zone, which is very much driven by avoiding winter. So the behavior is completely different. And the other thing that's true in the tropics is you can often have 2 seasons in a year. So you can have multiple growing seasons. That turns out to make a gigantic difference in terms of your outcomes. In the temperate zone, you rarely can get 2 seasons. You can rarely squeeze in 2 seasons in one calendar year. So these things make a huge difference. So the idea that you might have very different consequences in different parts of the world is definitely something worth exploring. And the idea that climate is not 2-dimensional, it's multi-dimensional, and it's complicated. I'm very sensitive to that. I think that is absolutely the case. And we're just beginning to understand it. So the idea there may be more things about the climate that we don't yet understand, I think that's worth exploring. So I encourage you to look at regional differences.
Perfect. Yeah. I totally agree. It's an important topic. Okay, the last question is, I leave it for now, maybe Enrico Turco, if he's able to switch on his camera and to ask the last question.
Yeah, can you
Yes.
hear me?
Yes.
Okay, thank you. Well, first of all, thank you for your interesting presentation. I have a small question about the underlying assumption of your panel analysis. If I understood correctly, a common assumption within the empirical literature on estimating the effects of climate change is that only the market sectors that are directly exposed to the weather, such as agriculture, energy, and water, are affected by climate change. This is about around 10% of GDP. However, we should take into account that these sectors are not isolated from the rest of the economy, but they are interrelated with other sectors that are not directly exposed to the weather, such as manufacturing and service, through input-output relationships. And once we consider these interactions and propagation mechanisms within the economy, the effects of climate change on GDP are likely to be larger than what we used to think. And if this is correct, empirical studies that focus only on exposed sectors are likely to underestimate the economic effects of climate change. What is your opinion on that? Would it be possible to include those interaction between different sectors in the economy inside an empirical analysis on the effects of climate change? Thank you.
That's a great question. There's always a vulnerability by looking at sectoral studies that it's a partial equilibrium analysis and that you've missed a general equilibrium consequence, which is what you're bringing out. It's possible that maybe interactions across sectors could make the effect on the GDP different than what the individual one at a time analyses suggest. So that was one of the reasons to do the GDP studies. So the analysis I presented today is looking at the entire GDP and is asking, what do you see across the entire GDP? And it's possible you could have seen much larger effects if they amplify through the GDP. So I agree with you, that's theoretically possible. But what I'm telling you, so that's why you want to study GDP. You want to make sure, okay, do you see this, or do you see something else, that you see a lot of substitution, so that in fact the things get smaller, not bigger, when you actually look at the entire economy. What the analysis is suggesting is that the effects look like they're on the same scale as what the sectoral studies suggested. You're getting results. When you do the analysis correctly, you're getting results which look similar to what the sectoral studies are saying. So although there may well be some interactions across sectors, for example, we know that water and agriculture are definitely interlinked, and that in some sense energy prices in agriculture are interlinked. It turns out that it doesn't look like those interlinkages change the results very much. Quantitatively, they don't seem to make a difference. So you're right, this is something that needs to be chased down, but that's exactly why you might want to do a GDP study like this one. is just to make sure that the sectoral studies haven't made a big mistake somehow by missing something. It's also true that we've been doing a lot of modeling on this. So the people that have used these things in macro models should have seen something like that if it was there. That should have popped up. I agree that it's always possible that we missed something that we should have had, but a lot of different people would have had to miss this if it's still true and we haven't seen it. So I think right now I would call that a theoretical possibility that looks like it's empirically not relevant.
Okay, thank you very much.
You're welcome.
Okay, thank you, Enrico. Now if we can close, I would like to thank you very much for having the honor to have listened to your presentation in your Q&A session. That was very, very interesting, I have to say. As I told you, I invite you when this will be possible here in film for the Enrico Mattei. Thank you very much. Thank you to all the participants.
Thank you for having me. I really appreciate it.
Thank you very much.
Thank you.
Bye-bye.
Bye.